Hi everyone, I'm Sangeeta Lakshmi, Assistant Professor of EC Department in R.M.K College of Engineering and Technology. I'm going to explain about the different biasing methods as well as small signal analysis in this presentation. So before that, you have to know the syllabus of Unit 1. So these are the syllabus in the Unit 1 BJT amplifier. So what are all the topics we are going to discuss today is, first we are going to see large signal analysis or DC analysis. In that we are going to see the different biasing methods. Then we are going to see small signal analysis, which is also called as AC analysis. So in that we are going to see what is the equivalent model of BJT and what its small signal parameter. So first of all, we start with the biasing method. What is biasing? First of all, we have to know what is biasing. Biasing means it is a process of giving the external DC supply to the transistor in order to operate the transistor in a desired region. Desired region means you know that we have three different modes of regions, which is cutoff, saturation as well as the active region. Out of these three regions, we all know that the BJT has to operate in the active region in order to act as the amplifier. So this is the biasing circuits which is required to make the transistor operate in a active region. So for the first method is, here we have the um, fixed or base resistor bias. The first method is called fixed bias or base resistor bias. The second one is voltage divided bias, and third one is collector to base feedback bias. See the first method, fixed bias. It is a simple circuit. In the simple circuit which contains DC source, that is VCC, and signal source VI. So in this, CC is the coupling capacitor. Always the coupling capacitor is used to isolate the signal source from the DC supply. You, as we all know that the capacitor allows only the AC signal, so it will allow only the AC signal, it will block the DC. So it is simple circuit which can be used to bias the BJT in a active mode. So if you want to that is go for the large signal analysis, we have to remove the signal source. I already told you the superposition principle, right? Superposition principle states that if the circuit contains multiple number of sources, the response of the circuit with the multiple source is equivalent to the sum of the response of the circuit with the individual source. So we are going to analyze the amplifier with DC voltage separately as well as AC voltage separately. So only with the analysis of DC supply, it is called as a large signal analysis, right? So the large signal analysis, we are going to use the different biasing methods, right? So in this method, we can see for the DC analysis, the capacitor will be exhibit the high reactance. High reactance means it will act as the open circuit. So that's why it is removed from the next circuit, right? The fixed bias method, we have removed the coupling capacitor as well as the signal source. So reminding what we have, this is the analysis only with the DC signal. So in this, we have to find out what is the base current, what is collector current, what is VCEQ. As we all know that the Q point is nothing but the collector current as well as VCE, right? ICQ as well as VCQ. These two are the Q point, right? So we have to find out the Q point values for each and every circuit. Move on to the next circuit, collector to base feedback bias. In this method, why we are going from fixed bias to collector to base feedback bias means, in the fixed bias, a simple method. So whenever there is a change in the collector current due to temperature, the Q point will be shifted to up or down. Always we want the Q point in the stable position. So always we want the Q point at the center of the DC load line. It should not change up. It should not change to closer to cutoff or else saturation region. Always it should be in the center of the DC load line in order to get the faithful amplification. But the fixed bias provides less stability because the Q point will be shifted sometimes due to the temperature variation. Because the collector current is depends upon the beta, next VBE, next parameter is IC naught. So these three parameters are depends upon the temperature. Whenever there is a temperature changes, these three parameters will change. That will affect the collector current so that the Q point will be shifted. So I want the Q point in a stable position. That's why we are going for the collector to base feedback bias. In this method, what happened? The current drawn through the collector resistance RC is IC plus IB. Whenever there is change in the collector current due to temperature, what happened? The IB current will be reduces. So IB current is reduces means obviously we know that IC equal to beta into IB. So IC will be reduces because IB is reduces. So by using the feedback, we can able to control the or stabilize the Q point at the fixed position. Since the IC is depends on the temperature, whenever there is change in the temperature, the collector current is increases. If the collector current increases, the Q point will be shifted. But in this collector to base feedback bias, even though the IC is changes due to the temperature, the IB is reduces. If IB is reduces, correspondingly IC will be reduces or back to form. So the Q point is in the stable position. And next method is voltage divided bias. Usually in all the circuits we are using the voltage divided bias. It is also called as self bias. So in this method, we have the R1 and R2 resistance, which is called as biasing resistor. As usual, here also we have the collector that is coupling capacitor, which will isolate the signal source from the DC supply. So this circuit is very complex to analysis. So we have to convert this voltage divided bias into simplified form, which contains the Thevenin's voltage. As we all know that Thevenin's theorem, if we have the complex circuit, that can be converted into simplified circuit by using the Thevenin's theorem, which is nothing but the Thevenin's voltage in series with the Thevenin resistance. So by using that theorem, we are converting this large circuit into simplified form for the further analysis. So with this, the biasing method is over. These are the common methods we are using for the all the books. Even we have some more biasing methods also available. The majority biasing method used in all the circuits are these all the methods. But most common is voltage divided bias. That is very much important. So next we are going to see the small signal analysis. Before that, we have to know these all the biasing methods only for the making the BJT to operate in a active mode. Okay, but due to temperature changes, even though we are designing the circuit, definitely there is a change in the Q point. So how to stabilize the Q point? We have more stabilization methods are available to stabilize the Q point. Okay, so next thing is we are going to see the small signal analysis. Small signal analysis means I told you we are going to analyze the amplifier only with the signal source, not with the DC source. We are setting the DC voltage to 0. So if you want to analyze the small signal analysis, we have to know the equivalent model of BJT. What is mean by model? Actually, model is nothing but the equation or circuit diagram which will describe the behavior of the device. So here we are also going to use the equivalent model. That model is called hybrid pi model. Many models are available. The hybrid pi model is very simple to analyze the BJT. So first one is NPN transistor. We all know that we have three terminals, base, collector and emitter. In the NPN transistor, the current flowing through the base as well as collector both will be added together, that both current will be flowing through the emitter terminal. The emitter terminal direction indicates the holes current flow, that is conventional current flow. Conventional current is depends upon the holes direction. So the direction is indicates the holes direction, not the electrons direction. Okay, so in this equivalent model you can see here we have the In between base and emitter, we have R.P resistance. Across the R.P resistance, we have the voltage which is called as V pi. The current to the R.P is IB. Okay, this is the input. Actually, the transistor can be treated as the two-port network. So, the input port is between base and emitter. The output port is between the collector and emitter. So, in between collector and emitter, we have the current source. That diagonal diagram is denotes the dependent current source, which is nothing but a Gm into V pi, right? So Gm is nothing but the inverse of the resistance. So V pi into Gm is nothing but the current source. Across it we have the R naught resistance. So towards base we have the IB current. Similarly towards collector we have the IC current. Both will be added together to flow through the emitter terminal. This is another circuit. The next to this circuit is another circuit, the same thing. Here we have used Gm into V pi current source. Here we have used beta into IB. Both are equal only. Gm into V pi is equivalent to beta into IB. The next one is the below is the PNP transistor. Here also we have the same base, collector and emitter terminal, but the current direction is inward. Here also the direction is indicates the conventional current direction, which is nothing but the holes direction. It's not the electrons, right? This is the important thing you have to know. So what is the equivalent for the PNP transistor is, see, please compare with the NPN transistor equivalent diagram as well as the PNP transistor equivalent diagram. Only thing is the current direction, right? In the NPN transistor, the current flow is from collector to emitter, whereas in the PNP transistor, the current is from emitter to collector. That is the only difference here. Okay, and also the voltage across R-Pi is, the polarity is changed, right? Here also instead of Gm into V pi, we can use beta into IB. The next is small signal parameters of BJT. So as we all know that we have the equivalent model which contains R-Pi resistance, R naught resistance and Gm into V pi, which is nothing but the current source. So we have to know these three parameters, right? First we start with the base diffusion resistance, which is nothing but the R-Pi. So R-Pi resistance is always is the ratio between the voltage and current. So here inverse of R-Pi is equivalent to change in IB current with respect to change in VBE voltage. Here IB is nothing but the, actually IC is equivalent to beta into IB. So IB equal to IC by beta. We know that IC equal to IS in exponential of VBE by VT. Here IS is the saturation current, VB is the voltage between base and emitter, and VT is the thermal voltage, which is nothing but a 26 millivolt. So here instead of IB, I have to substitute IS by beta in exponential of VBE by VT. If I am differentiating this whole expression with respect to VBE, I will get 1 by VT into IS by beta in exponential of VBE by VT. As we know that IS by beta in exponential of VB by VT is nothing but the IC naught by beta, right? ICQ by beta. So R pi is nothing but the beta into Vt by ICQ. ICQ is nothing but the collector current at Q point, that is quiescent point. Okay. So this equation is very much important. You have to remember this. R pi equal to, that is beta times the voltage by current. Okay. The next small signal parameter is transconductance Gm. So Gm is the change in collector current with respect to VBE, because conductance means current by voltage. Transconductance means output current by input voltage. Output current is IC, input voltage is VBE. That's why we have the dou IC by dou VBE. See here also IC is equivalent to IS in the exponential of VBE by VT. So if you are differentiating this expression with respect to VBE, you will get 1 by VT into the same I is exponential of VBE by VT. So as you already know what is ICQ, so thus expression can be simplified into ICQ by VT. So GM equal to ICQ by VT. As we all already know, conductance means current by voltage. So transconductance means ICQ by VT. This is also important signal parameter we have to remember. The last small signal parameter of BJT is the output resistance R0. So which is, we already know that R0 is nothing but the resistance. So voltage by current is the resistance. Here inverse of R0 is equal to collector current with respect to VCE. So if we are differentiating IC, that is collector current with respect to VCE, you will be getting what? That is IS in the exponential of VB by VT into 1 plus VCE by VA is nothing but the collector current. Actually, collector current is independent of the VCE. But why we have included the second term 1 plus VCE by VA is, this indicates that we have included the yearly effect. What is mean by yearly effect? Actually, as we all know that if you want to operate the BJT in active mode, the base and emitter should be forward bias and base and collector should be reverse bias. So if we are reverse bias the base and collector, more and more voltage, what happened? The base width will be modulated. So that effect is called as base width modulation or yearly effect. This will happen when VC is attained to larger yearly voltage. So this effect we have included here. So after this including yearly effect, if we are differentiating this whole collector current with respect to VCE, you will be getting 1 by VA into IS exponential of VBE by VT. So finally it is simplified to ICQ by VA. Thereby what is R0? R0 inverse is ICQ by VA, but R0 equal to VA by ICQ. So VA is nothing but the early voltage and ICQ is the collector current at quiescent point. Okay. The next parameter is common emitter current gain beta. Right. So beta is nothing but the GM into R pi. See here, GM is transconductance and R pi is the base diffusion resistance. If you are multiplying both, you will be getting beta, right? So GM into R pi is nothing but the beta.